folks. Welcome to
Vector calculus.
What's up, folks? Welcome back to the next lecture in vector calculus. Today I'm going to show you something magical. Let's check it out with the problem we've got today. Today we're going to find the distance between a point and a line, alright? Or rather a point and a plane. I don't even know what I'm talking about. So, find the distance from this point Q to this plane 3x minus y plus 2z equals 6. Alright, now the first question you're asking me is, how do you know Q is a point and how do you know this is a plane? Well, to answer your question, go ahead and watch lecture number 43. That's going to answer how you can recognize points, planes, vectors, and lines in 3D. But just to give you a quick summary, I know that Q is a point because it has three coordinates. It has an x coordinate 1, a y coordinate 5, and a z coordinate -4. And I know that this equation right here represents a plane because it's in the form of ax, by, cz, d. Alright? That's how I know that's a point. That's how I know that's a plane. How do you find the distance between a point and a plane? That's the key question we got today. Alright, so the first thing I want to do is just to give you a visualization. So let's move it over here. Alright. Now, when it comes to these kinds of problems, you always want to draw a picture. You're never going to remember the formula. Never. Trust me, unless you're some kind of a, those photographic memories, which I don't have, you probably don't have either. So the first thing you want to do is draw a picture. And I want to draw a good picture for you today. So here's the picture we're looking at today. Alright? So here's my picture. And that right there represents a plane. Alright? A plane, of course, extends in all directions infinitely. But, just for the sake of illustration, here's my plane. Alright, that's my plane. Where's my point? Well, I'll just draw a point somewhere. I don't know. Maybe here's my point. This is my point, 1, 5, -4. Okay. Well, how do I find the distance between these two? Well, I'm not sure how you find the distance, but here's how you can try. You can find a point on the plane. How do you find a point on the plane, you're asking? Well, just plug in some numbers that give you 6, right? Maybe 2, 0, 0. If you put 2 in for x and 0 for y and z, you'll get 6. So maybe this is that point. Maybe, I don't know. This is maybe that point, 2, 0, 0. And connect your original point and that point on the plane. Alright? So connect these two guys and you'll get a vector. Something that looks like that. Okay, but that's still not the distance, right? Because the distance between two things is the shortest path between them. This right here clearly isn't the shortest path. If this is your home and this is your school, you aren't arriving at 8 a.m. Oh, hell no. So, what is the distance? Well, the distance is this distance. But how do you find that? Well, remember that if you're given the equation of a plane, you automatically know the perpendicular normal vector to that plane. Right? Let me redraw that perpendicular normal vector. If you're given the equation of a plane, you automatically know the normal vector to that plane, right? Remember, the components of the normal vector match the coefficients of your plane. And so now you can project this kind of a vector between your initial point and the point on the plane. Take this vector, project it onto the normal vector, and you'll end up with a vector that might look like this. A vector that might look like this, right? Your normal vector might be very small. It might be this. But your projection is the real distance. Alright? That right there is the real distance between your point and the plane. Now I'm going to explain that again. This time, let's see if you can follow it. Alright? So let's try to do that explanation again. This time I'm going to start with a different plane, just to give you a different sense of perspective. Let's start with a plane maybe somewhere here. Alright, so here's my plane, and here's my point. And I want to find the distance between my plane and my point. Well, as you know by now, take a point on the plane, Alright, connect these two. Wow, what a horrible miss. Connect these two guys so that you get a kind of vector. And once you have this vector, what do you want to do once you have the vector connecting your original point and the point on the plane is you want to take this line and project it onto the normal vector. Okay, so then you're going to get the distance. You're going to get the distance, and that distance is going to be given by the projection of this vector onto the normal vector. Hopefully you get that. If you don't, just leave comments down in the section below and I'll be happy to answer them. Alright, so now it's time to put our ideas to the test. Okay, here we have our point and here we have our plane. So let's draw our plane nicely and let's draw our point nicely. Okay, so what is our point? It's 1 comma 5 comma minus 4, 1 comma 5 comma minus 4. Once again my marker's dying out, but hopefully it'll survive. And of course my plane is 3x minus y plus 2z equals 6. Now I want to find the distance between these two guys. I gotta get a point on the plane. Maybe somewhere here. Well, I want to settle for the easiest point. So how about 2, 0, 0? If I put 2 in for x, 0 in for y, and 0 in for z, do I get 6 on the other side? Well, check it out. 3 times 2 is going to give me 6. 0 is going to give me 0. 2 times 0 is 0. And so yes, I do indeed get 6. So here's the point I picked. It's 2, 0, 0. And yes, it does indeed lie on the plane, which I just showed you. I just showed you by substituting these numbers, these coordinates. Now, I also know the normal vector coming out of my plane. What's that normal vector going to be? Well, that normal vector, the components of that normal vector are just going to be given by the coefficients of my plane. Right? What are the components of that normal vector? Well, they're simply going to be 3 comma minus 1 comma 2, which come from the coefficients of my plane. If you don't know why that works, just go ahead and watch our lecture on normal vectors and planes. Alright? And of course, connect these two points to get your own vector. Right? Connect these two guys, you're going to get another vector. And what is that vector? Well, just subtract the coordinates. 2 minus 1 is 1. 0 minus 5 is negative 5. And 0 minus negative 4 is 4. So there's my vector. There's my two vectors. Now, all I need to do is project this vector onto my normal vector. Let's call this vector A, and let's call my normal vector N. Alright? So now what I'm really looking for right here, is the projection. The projection of my vector A onto the normal vector. Now what's the projection formula? Well, hopefully you remember. The projection formula tells us that the projection of A onto N is going to be their dot product over the magnitude of my normal vector times the direction of my normal vector, which is given by this component. But we just want the distance. Remember, distance is a scalar property. It's just a number. It's not a vector. The projection is a vector, but we don't need a vector. We just need a scalar quantity that gives us the distance between the point and the plane. So how do we do that? Well, let me show you. What we really need to discard is this kind of vector quantity here. We can just send this to the garbage can because we don't need it, alright? We don't need that thing because we don't want a vector. At the end of the day, what we want is a scalar quantity that represents distance. And of course, distance is just a number. It doesn't involve any vectors. That's why we send this thing to the garbage can. Okay. And so now all I have to do is just find the projection. Okay, let's go ahead and switch markers. It's time to switch markers. Alright, so what is my projection going to be? What's my projection going to be? Well, I'm going to have the projection of A onto N. Well, first thing I need to do is take their dot product. So I'll just put this away for now. make sure I explain every step. Okay, so projection of A onto n is going to involve their dot product. So it's going to involve the dot product of 1, -5, and 4 with 3, -1, and 2. Divide all of that by the magnitude of my normal vector. That's going to be the square root of 3 squared plus -1 squared plus 2 squared. And so the projection of A onto n is going to be what? Well, I'm going to have 1 times 3 plus -5 times -1 plus 4 times 2 for my dot product. And then divide all of that by the magnitude of my normal vector, which is going to be 3 squared, which is 9, -1 squared is 1, and 2 squared is 4. And so I'm going to conclude with the projection of A onto n. And what is that? Well, 1 times 3 is just 3. -5 times -1 is just 5. 4 times 2 is 8. Divide all of that by 9 plus 1 is 10, plus 1 is 14. And so my final projection is going to have a total magnitude of what? Well, 3 plus 5 is 8, plus another 8 is 16. And so the projection of A onto n is just going to be 16 over root 14. And that, ladies and gentlemen, is going to be the distance between my point and my plane. Remember, my point was 1, 5, -4, and my plane was 3x minus y plus 2z equals 6. And so the distance between these guys was just a good old rational number, 16 over root 14. Let's recap how we did that. Let's recap the steps we took. Okay? Our problem was to find the distance between this point and this plane. Alright? So what we did was we found a point on our plane, connected that with our original point, projected that vector onto the normal vector, and used the projection formula to get the distance between our point and our plane. Alright folks, that's it for this lecture on vector calculus. We'll check you out next time.
Ambition plus MKO plus scaffolding equals learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today. And the first 50 of you to use that link will get a 20% discount on the Brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.